Okay, Chapter 1, Section 6, the design of experiments. Okay, in this section we're going to cover the characteristics of the experiments. We're going to explain the steps in designing an experiment. We're going to explain complete randomized designs, matched pair designs, and explain randomized blocking designs. Okay, so an experiment is a controlled study conducted to determine the effects of varying one or more explanatory variables, called factors as well, um, on the response variable. Any combination of values of the factors is called a treatment. Okay, so the experimental unit or subject is typically a person, or it could be an object, it could be an animal. It depends from experiment to experiment. It's some well-defined item on which a treatment is going to be applied. A control group serves as a baseline treatment that can be used to compare other treatments. And a placebo is an innocuous medication, typically, such as a sugar tablet that looks and tastes and smells just like the experimental medication. It doesn't have to be a medication. It's just something that prevents the person that's receiving the treatment from knowing whether or not they're receiving the actual treatment or if they are themselves acting as a control. If they're part of the control group or if they're part of the group of people that are receiving the treatment. Okay. Blinding refers to the non-disclosure of the treatment an experimental unit is receiving. Right? So blinding just refers to the fact that the person doesn't know whether they're receiving the treatment or not, typically medication, right? So the placebo effect is a well-known phenomenon where people feel they're feeling better because they think that they are receiving medication. Blinding refers to cases where they don't know themselves whether they're receiving the medication or not. Single blinding means that the person doesn't know that whether they're receiving the medication or not, whether they're part of the treatment group or they're part of the control group. And double blinding refers to both the person being experimented on, the subjects not knowing, as well as the people in charge of the control group, say the doctors that are conducting the experiment, that they themselves also do not know who's in the control group and who is in the treatment group. Right. This is again to prevent any bias from happening from the doctors or the people in charge of the experiment. Okay. So, for example, the English department of a community college is considering adopting an online version of a freshman English course. To compare the new online course to the traditional course, an English department faculty member randomly splits a section of her course. Half the students receive the traditional course and the other half is given an online version. At the end of the semester, both groups will be given a test to determine which performed better. Okay, so who are the experimental units? Well, clearly the students are the experimental units, right? What is the population? What is the population for which the study applies? And this would be her class, right? This experiment applies to her class. What are the treatments? We have two treatments in this situation. We have a traditional course, and the other treatment is the experimental course. What is the response variable? The response variable is the scores on this exam at the end to determine which of the treatments did better. Right? Why can't this experiment be conducted with blinding? Well, obviously the students themselves will know whether they are taking an online platform or if they are doing a traditional course. Right, so it's in this case not possible to do blinding. As far as the person doing the results, I guess it's possible that somebody that person doesn't know whether the exam in front of them comes from someone who was part of the online course or part of the traditional course. So that person can sort of be blinded from that part of it. Good. So single blinding from the person grading the test can be possible, but blinding for the experimental units is not possible in this little case. Okay, good. Let's just both students and instructor know which. Okay. To design an experiment means to describe the overall plan in conducting the experiment. There's several steps that this author recommends. So step 1, identify the problem to be solved. So clearly identify, in an explicit manner, the problem you want to solve. Should provide experimental direction. Should identify the response variables in the population to be studied, and often referred to as the claim, right? So what is it you want to test? 2, determine the factors that affect the response variable. So once the factors are identified, it must be determined which factors can be are to be fixed to some predetermined level, right? The control. Which factors will be manipulated and which factors are uncontrolled. 3, determine the number of experimental units. As a general rule, we want to choose as many experimental units as time and money will allow. Techniques exist for determining sample size, provided certain information is available as well. Determine the level of the predictor variables, right? This is the control. There are 2 ways to control the factors. One, we can set the level of the factor to 1 level throughout the experiment. If you're not interested in its effect on the response variable. 2, we can set the level of the factor at various levels if you're interested in its effect on the response variable. The combination of levels of all the varied factors constitute the treatments in the experiment. Good. So think, for example, of like temperatures. If this is like indoors and you can control the temperature, do you want to try at different temperature levels to see how things affect the experiment? Or do you just want to leave it at the same temperature for all the different treatments? That would be one example. Maybe gender would be another example. If you just want to separate by gender and then have males do something, females do something else, and that way you can control for those factors. Okay, determine the level of the predictor variables. So randomize. So randomize the experimental units to various treatment groups so that the effect of variables whose level cannot be controlled is minimized. The idea that randomization averages out the effects of uncontrolled predictor variables. Okay, so for example, let's throw out an example to kind of apply some of these. Let's say we're a dairy farm and we're interested in determining increasing milk production from our cows. And maybe we are looking into various diets. Maybe diet A is all corn. Diet B is half corn, half wheat. And we want to see which of those diets ultimately produces the most amount of milk, right? So we have our cows, and we can just randomly assign cows to diet A or diet B, right? And there's a lot of factors other than the diet that will affect milk production, of course. The actual type of cows, maybe they vary. There's genetics, exercise, the age of the cow. A variety of things affect the actual milk production. But if we just randomly assign cows to one treatment group versus another treatment group, then all those other uncontrolled things just kind of balance themselves out. Like, for example, age is one big factor that will determine how much milk is being produced, right? I don't really know anything about cows, so I'm not really sure what the optimal age is for milk production of cows, but I'm sure that it does affect milk production. But if you just randomly assign cows from one group to another group to another group, then both groups will hopefully get a pretty good varied mixture of younger cows and older cows into both groups. That way, things kind of cancel themselves out, and it doesn't turn out to be such a huge, impact. Provided you have a fairly large number of cows, you should be able to do that. Good, 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 good. Let's see. Right, so that's what they mean here. Randomize the experimental units to various treatment groups so that the effects of various variables whose levels cannot be controlled is minimized. Right, so like I said, age in the cows is a really big factor. But if we just randomly assign them to to both groups, hopefully that kind of gets averaged out. The idea of randomization averages out the effects. Okay. Replication occurs when each treatment is applied to more than one experimental unit. This helps to assure that the effects of the treatment is not due to some characteristic of a single experimental unit. It is recommended that each treatment group have the same number of experimental units. Right. So again, in my little milk cow example, you want to have as many cows assigned to each group as possible, and you want to apply the treatment, which in this case would be the diet, to as many cows as possible. If you only do it to one cow, then it's difficult to conclude that your diet is exactly the result of whatever output you get, because there's only one cow. So there could be some other factor out there, some other reason why you're getting the results that you get, and it might not be necessarily connected to the diet that you're giving the cow. Right? If I only have 2 cows, I only have 4 cows, and I assign 2 cows to one treatment and 2 cows to another treatment, and I give a diet to these 2 cows over here, and then another diet to these other 2 cows, and then I get a certain response, it would be easy to doubt the results because there's only 2 cows, and maybe it just so happens that in one group 2 cows are very young, and another group the other 2 cows are much older, and that has a big impact on the results. Right? It could also be that maybe the type of cows they are. There could be some other factor there. It could be how long ago did they have a calf. Right? That's a baby cow, I think. So if we're looking at a cow that recently, within a few months, gave birth to a baby calf, maybe that affects milk production, versus one that has not given birth to a baby cow, or it's been a very long time. So all these things might have an impact on our results. So we want to do replication. We want to apply our treatment to as many cows as possible to counteract some of these other uncontrolled factors. Good. So we want to conduct our experiment. We want to collect and process the data by measuring the value of the response variables for each replication. So in my little idea of the cows, the response variable would be the milk production. The explanatory variable would be the diet that I provide them. And then there would be these other factors that are uncontrolled, such as weather. Maybe the weather has something to do with milk production. Maybe the moisture level has something in the air, has something to do with it. How about exercise? Maybe if I just leave my cows alone out in the yard, maybe some cows just naturally walk around a lot and have a lot of exercise, and maybe some cows are kind of lazy, and maybe that has something to do with milk production. Right? So there's a variety of factors out there that might impact my milk production that I might not be taking into consideration. Okay, so collect the data. So test the claim. This is the subject of inferential statistics, right? So we're going to collect our data, and then we're going to use techniques that we learn in inferential statistics down the road in order to be able to make claims about the population based on the sample results that we're getting. Based on our experimental results, can we make rational conclusions about the population of the larger population? Right? So in my little experiment of cows, maybe I have 50 cows and I break them up into 2 groups. I do my treatment, I get my results, And now I want to make a claim not just about my 50 cows, but I want to make a claim about all cows out there, and how I can improve milk production based on diets, right? Do I want to be able to conclude that one diet results in more or less milk production? Okay. A completely randomized design is one in which each experimental unit is randomly assigned to the treatment. Right? That's pretty self-evident. For example, the octane of fuel is a measure of its resistance to detonation, with a higher number of indicating the higher resistance. An engineer wants to know whether the level of octane in gasoline affects the gas mileage of an automobile. So let's think about how to design an experiment associated with this. So our response variable in this situation is going to be the miles per gallon. How many miles were we able to get out of the vehicle? The factors that affect the miles per gallon, the one we're focusing on, is of course the actual octane level of the gasoline, but also the engine size will affect the miles per gallon. The temperature outside will affect miles per gallon. Driving style, driving conditions, characteristics of the car, whether you have the air conditioning on or not, also can affect the miles per gallon. So a variety of factors can affect miles per gallon. Okay, so let's say we get 12 cars, all of the same model in the same year, so they're as close to being identical as possible. Though even then they're not identical, right? There's always going to be slight differences from one car to another as they're being manufactured. There's always going to be slight differences in the vehicles. So let's list the variables and their levels. So the octane level is the one we're most interested in, right? That's the explanatory variable. And we're going to manipulate it in 3 ways. So there's going to be 3 different treatments. We have 87 octane, 89 octane, and 92 octane. Right? So we have 3 different treatments that we want to apply. Another variable, another factor is the engine size. And we can say that they're approximately the same engines if we pick the cars to all be the same model in the same year. The temperature when this experiment occurs, well, if you do it all at the same time, if you are going to conduct the experiment and all 12 cars drive at the same time, they're going to experience the same temperature outside. However, if you're going to do this one car at a time, then that becomes a bigger issue, right? Because if you take car number 1 and do this whole experiment, that might take you an hour, and then you do car number 2 and car number 3. By the time you get to the last car, you might experience a very, very different temperatures, right? So the conditions might change. So if you do them all at the same time, though, then they all experience the same temperature, and whether it's hot or cold, whether that makes it easier or more difficult to get good mileage, it's not going to affect our results because all 12 cars are getting the same temperature. Okay, driving style and conditions. All 12 cars will be driven under the same conditions on a closed track. So that'll be fixed since we have a specific track and you identify how the drivers are going to be driving. So that can be fixed. And then other characteristics of the cars are, of course, the model, the year, and even though that there are slight variations from car to car, we can assume that they're approximately the same. But in order to further eliminate minor differences between the cars, we can do a randomization, right? Randomly assign the cars to the 3 different groups. So we can assign 4 cars to each treatment group in a randomized way, and then that again helps us make sure that any differences between the actual cars sort of gets neutralized. Good. All right. So we'll randomly assign 4 cars to the 87 octane, 4 cars to the 89 octane, 4 cars to the 92 octane, and then give each car 3 gallons of gas, drive the car until they run out of gas, and compute the miles per gallon. Okay, and then determine whether any differences exist in miles per gallon. So here's a nice little diagram of this particular experiment, right? So here are 12 cars, randomly assigned four cars, give them the different treatments, which are the different octanes, and then compare the miles per gallon. Good. So this is one way to do this. One criticism could be that um, this test track might not be, uh, you might not get the same results in real world driving, right? Real world driving has a lot of stopping and going, traffic, and a fixed track doesn't really have the same conditions, right? So that could be one criticism. So if we wanted to do something different, like okay, let's do real world driving, then it might be a little bit more difficult to be consistent with the driving style, right? Even if you have all 12 cars on the road at the same time, it might be hard to keep them together. Eventually, lights hitting a red light and stuff might separate the cars, and so some cars might experience a lot more stopping and going versus another car, and that could affect your results. Good, good, good. Okay, so lots of stuff to think about. Another popular type of experiment is called the matched pair design. And this is a design in which experimental units are paired up, and they're paired up or matched up in based on some sort of relationship that might have. Often the relationship is that it's the same person. So there might be a before and after kind of situation. Maybe you give somebody a quiz and then you show them a movie or something. That's maybe like an educational thing or a documentary or something. And then you give them a quiz at the end to see if there's any difference, to see if there was any impact from watching whatever you showed them. So you have a before and an after results for each individual person, right? So it wouldn't make sense to just have all the quizzes from before and have like an average quiz score, and then have all the quizzes after and have an average quiz score. It would make sense to pair up the individual quizzes from each individual person to see if there's a difference between them, if they got the same score before and after, or if somehow there's a difference between them in either direction. Good. So it's often the same person. It's often a before and after kind of thing. Or it could be two twins. That's always very popular as well. It could be a husband and wife kind of thing. It could be a father and son kind of thing. So somehow they're connected to each other, and we want to group up those two data points and see how they differ. Right? One really famous example that happened recently is astronauts Mark Kelly and Scott Kelly are twin astronauts. And so one of them, I believe it was Scott, I'm not really sure which one. One of them was sent into outer space for a year, and we measured all his biostats before, and a lot of them during and when he came back. And then we also compared that to his twin brother to see how they differed. What was the impact of living in outer space for a year? So it's a lot of. They made a whole documentary. I think it's on Netflix. If you guys have some time, it's really really interesting. Anyway, so that's a matched pair experiment. Here's another example of a matched pair design. So xylitol has proven effective in preventing dental cavities when included in food or gum. A total of 75 Peruvian children were given milk with and without xylitol and were asked to evaluate the taste of each. Okay, so we're not determining whether the xylitol is good at preventing cavities in this experiment. We're just simply looking at the taste. The researchers measured the children's ratings on the two types of milk, right? One milk has xylitol and one milk does not. The response variable in this experiment is the ratings, right? They're going to identify which milk they like the most or the least or the same, some sort of numerical ranking to each milk as the children taste them. And of course, this is a matched pair because each child is given both milks, one milk with and one milk without xylitol. And we're trying to see the difference in scores between the two is what's important, right? Because, I mean, maybe a kid just doesn't like milk and doesn't like either one of them. Or maybe a kid really likes milk and likes both of them. And in both of those cases, nothing interesting happens. We really care about the cases where there is a difference in scores, where the child has a preference for one or the other. So we want to keep the scores together. We don't want to just say, "Oh, here are all the scores for all the milk cases. These are all the ratings for the cases where it was just milk by itself, and here's all the ratings for all the cases where there was xylitol in the milk." We want to match them up and pair them up and see if there's a difference between them. Good, good, good. Okay, what are the treatments? Well, there's two in this case, milk with xylitol, milk without xylitol, right? So there's two treatments. This is a matched pair design, and the experimental units are the 75 Peruvian children. Why would it be a good idea to randomly assign whether the child drinks the milk or the xylitol first? Okay, so we want to remove the effects of the order in which the milk is drunk. Right, so you don't want to always assign the glass with just milk to always be drunk first, and then the glass that has the milk and xylitol second. You don't want to establish a particular order every time, because that might affect the results, right? So you want to randomize in which order the children got to taste the milks, right? Like maybe, for example, let's say the xylitol really does have a strong sort of taste to it, and so strong that when you taste it first and then you go back to just the milk by itself, there's still residual taste in your mouth from the first one, and so it might impact the score of the child on the glass that just has the milk by itself. Good, good, good. So you want to randomize the order as well. Do you think it would be a good idea to do a double blind on this experiment? And yes, right? So you don't want to have the children know, of course, that you don't want them to know which one has the xylitol and which one doesn't. There would be a predetermined conception in their heads of whether or not it's going to be good or not. So if you tell them, here's the glass that has the xylitol, they might intentionally decide that they don't like it. So of course you don't want them to know. And the person doing the experiment might also give them a sense of whether one glass has the xylitol or not. And so they might pass on that idea to the children. So it would be important in this case for both of them to not know which one has the xylitol and which one doesn't, right? A double blind experiment. Okay, almost done. Grouping together similar or homogeneous experimental units and then randomly assigning the experimental units within each group to a treatment is called blocking. So each group of homogeneous individuals is called a block, right? So if you can group up your sample, right? So you have your sample. Let's go back to my cows. Say I have a sample of 50 cows that I'm going to do my experiment on. There might be some unique characteristic factor that I want to sort of take into consideration. So age, we looked at that before. So I might group them up on based on age. So the younger ones, the middle-aged ones, and the older cows. And then when I have the three different groups, maybe to each individual group, I want to give them the two different diets. That could be one thing. There could be different types of cows. Big cows that are, I don't know, black. There's brown cows. I don't know. There's different kinds of cows. I don't know anything about cows. But there's different types of cows out there, so you can just group them up into different types, and then again apply the treatments to each individual group. It could be the weight of the cows. Some cows might be overweight for whatever type of cow they are. Some of them are overweight and some of them are not. Maybe that has something to do with the milk production. So there's a variety of things, factors out there, and as long as there's something similar, we can group up similar ones and then apply our treatments to both, right? Confounding occurs when the effect of two factors, explanatory variables, on a response factor cannot be distinguished. If we're unable to separate them, then we call that confounding. Okay, so here is, a randomized block design is used when experimental images are divided into homogeneous groups called blocks. Within each block, the experimental units are randomly assigned to treatments. Right? So, for example, going back to that English department that is considering adopting online versions of freshman English courses, after some deliberation, the English department thinks that there may be a difference in the performance of men versus women, so in the traditional and the online courses. So to accommodate any potential differences, they randomly assign half of the 60 men to each of the two courses, as they do the same for the 70 women, right? So we could separate them into different blocks, which are in this case gender, right? So that's what they have. That's the homogeneous element that they have in common here, their gender. These are all males, these are all females. And then once we have all the men separated into block number one, now we randomly assign these 60 men into either taking the online course or taking the traditional course. And then we compare, and we compare just these. We compare the results of the men only to each other, and we compare online versus traditional. And then separate from that, we have a different block over here, which is all the women. And then these 70 women are randomly assigned to this group or this group, where they will either receive the online education or they will receive the traditional course. And then again, we take their exams and we compare their exam scores just within that block. What we would not want to do is to compare scores across the two blocks over here. So we wouldn't want to compare those. Good. All right, that's it for section 6. So that's the end of chapter 6. Let's move on to chapter 2.
All right, let's continue with chapter 2. Chapter 2 is about using data, or taking our data and finding ways to present it, organizing and summarizing the data and presenting it in ways that viewers can digest the data, understand it, and maybe even have a little fun with it, depending on what the data is and how you're presenting it. So for us, that'll take a variety of forms, but just to kind of get a sense of what the pros are doing, let's watch a little presentation I found, a TED Talk, that does a really good job of showing you what the possibilities are. So I queued it up already.
Visualization is right at the heart of my own work too. I teach global health. And I know having the data is not enough. I have to show it in ways people both enjoy and understand. Now, I'm going to try something I've never done before. Animating the data in real space, with a bit of technical assistance from the crew.
So, here we go. First, an axis for health. Life expectancy, from 25 years to 75 years. And down here, an axis for wealth, income per person, $400, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now, I'm going to show you the world 200 years ago, in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest. But the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now, we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe! And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948. 1948 was a great year. The war was over, Sweden. The differences between the countries of the world was wider than ever. The United States was in the front, Japan was catching up. Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh, and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up with the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics. Most people today live in the middle, but there are huge differences at the same time between the best of countries and the worst of countries. And there are also huge inequalities within countries. These bubbles show country averages, but I can split them. Take China, I can split it into provinces. There goes Shanghai. It has the same wealth and health as Italy today. And there is the poor inland province Guizhou. It is like Pakistan. And if I split it further, the rural parts are like Ghana in Africa.
And yet, despite the enormous disparities today, we have seen 200 years of remarkable progress. That huge historical gap between the West and the rest is now closing. We have become an entirely new converging world. And I see a clear trend into the future. With aid, trade, green technology and peace, it's fully possible that everyone can make it to the healthy, wealthy corner.
Okay, so that's just a nice sample of how you can use data and present it in a way that is interesting, fun, very educational, and I don't know if you caught all the information that's presented there, right? We have colors to represent different regions of the world. We had a horizontal graph to indicate wealth, average wealth per person, I would assume. We have a vertical bar that was life expectancy. We had individual bubbles, and the size of the bubble represented the size of the population for that particular country. So we were connecting area, the area of a circle to population size. So there's a lot of information growing there. And then we had a time lapse, right? We had a counter starting from 1800 up to modern times. So we had time tied into the whole thing, and we can see how everything moves, and we were able to digest all that data and get a sense or an idea of what was happening from watching that graphical representation. An important note is that we had very few actual numbers there, right? Even though I could see the general trend and what's happening, and I got a sense of what's been happening over the past couple of hundred years, you couldn't really actually see the actual numbers, right? I don't really know what the population of any one of those countries was in 1800. I just know the bubbles, the sizes of the bubbles, and how that kind of has changed over time. And so the graphical representations that we go through often miss out on those minute details, like the finer points. Someone watching or observing, digesting your graphs is going to miss out on specificity, right? They may not be able to get the exact values out of it. And we're trading that precision in exchange for being able to get a good sense of a pattern, a trend, out of the data, right? So we're searching for trends and patterns that can be visually digested rather than the specific numbers that can be calculated and tabulated and get a very precise result, right? So we're exchanging precision away in exchange for being able to get a good sense of the data and what's happening with it. Okay, so that was the professionals. We instead are going to focus on a couple more simple tasks. We're going to learn about bar graphs and pie graphs. We're going to learn how to organize qualitative data in this section. So first of all, remember qualitative data means it's non-numerical data, so that's where we're going to start. Okay, when data is collected from a survey or design experiment, they must be organized into manageable form. Data that is not organized is referred to as raw data, right? Unorganized data is raw data. Once we organize it in some fashion, then we can present it in the forms of either tables or graphs or numerical summaries. Okay, a frequency distribution lists each category of the data and the number of occurrences for each category of the data. Remember, we're looking for qualitative data, which means that it's non-numerical in nature. For example, if we just ask people what their favorite color is, right? The results are just going to be a bunch of colors. We're not going to get any actual numbers that we can do math with. Okay. All right, so here's an example. The data on the next slide represents the color of M&Ms in a bag of plain M&Ms. Construct a frequency distribution of colors of plain M&Ms. Okay, so here is the data. Brown, brown, yellow, red, 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 brown, orange, blue, green, blue, brown, yellow, right? So here it is, just a bunch of raw data. This is what we consider raw data. And again, it's qualitative. It's non-numerical in nature, right? There's no arithmetic that we can do with this stuff. Okay. All right. So what we're going to do is do a tally for it, a tabulation. We want to write down each of the different types of colors that we see. There was a brown, yellow, red, orange, blue, green, right? So these are the colors that were part of my raw data. The colors that are not in my raw data are not going to be on here. Obviously, there was no black ones, so black is not a color on here. There were no purple ones, no purples, so we wouldn't put purple on there either. Okay, brown, yellow, red, orange, blue, green, and then we do a tally, right? Keep track of how many there were. So as we go through our raw data, we just put a little dash to keep track of how many times we've seen that. So brown, brown, yellow, red, right? That's how this little tally is constructed. I think that's pretty self-evident. Once you go through the whole data, we can keep track. We're able to figure out the frequency of each one. Frequency is how many times did it occur, the total number of times that that particular color appeared in the data. So a frequency of 12 means that brown appeared 12 times in this list, right? So we can just find it real quick here. So let's circle it. So brown, there's 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, 10, 11, 12. There. So there were 12 brown ones that appeared, and that's why we have a frequency of 12. Good, good, good. Okay, I think that's pretty self-evident. So once we create this tally, then we like to organize our results and just have a frequency distribution table, right? So where are we at? What was I going to do? A frequency distribution table. So traditionally in a frequency distribution table, this tally part is just kind of ignored. This is sort of side work. So you would kind of erase this part here and then just have your table that has the list of the colors and then the frequencies. How often did it appear? Good. Okay. A relative frequency is the proportion or the percentage of observations within a category and is found using the following table. So we're going to take the sum of all the frequencies. That means it's the total number of M&Ms in our M&M example. So we're going to divide the frequency of each color divided by the total of M&Ms, and that'll tell you what proportion occurred for each individual color, right? A relative frequency distribution lists each category of the data with relative frequency. Okay, so for example, back to our table, we have brown, yellow, red, orange, blue, and green. Good. And we had our results. Okay, so let's ignore this part here. We had our frequencies. So there were 12 brown ones, 10 yellow, 9 red, 6 orange, 3 blue, 5 green. So what we're going to do is add all of these up and figure out what the sum is. And put it in there. So if we add all of these up, we have 8, 14, 23, 23, 33, 45. Looks like a total of 45. Okay, so now we're going to come back and we're going to divide each of the frequencies for each of the categories by 45. So 12 divided by 45 is going to give you this decimal. And then 10 divided by 45 is going to give you this decimal. 10 divided by 45 is going to give you this decimal. And so on and so forth. So we divide all of them, and we end up getting these. So what these are is that these are proportions of that color. We could say that 26.67%, 26.67% of all the M&Ms in my batch were brown. Good. And 22.22% of all the M&Ms in my batch were yellow. Right? So proportions, ratios, relative frequency, these are all synonymous with each other. Good. Obviously, then, that must mean that the sum of all of these, if we add all of these up, they must add up to 1, right? Or 100%. Cool. Cool, cool. Okay, so frequency is how many there were, how often did that particular type of thing appear. So in this case, brown M&Ms. How often that category appeared in the entire sample. Whereas relative frequency is the proportion, right? The ratio of those. Good. So then we'll have a relative frequency distribution table. Good, 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 good. Okay, that's pretty easy. A bar graph. A bar graph is constructed by labeling each category of the data on either the horizontal or vertical axis and the frequency or relative frequency of the category on the other axes. Rectangles of equal width are drawn for each category. The height of each rectangle represents the category's frequency or relative frequency. Okay, so that seems pretty self-explanatory. Let's do a bar graph for our table, for our results for M&Ms, for our M&M data. Okay, so remember that we had this table, the frequency distribution table. So brown, yellow, red, orange appeared 10, 12, 10, 9. Okay, so this is our table. So if we wanted to turn it into a bar graph, it would look like this. So little rectangular bars. Notice, very important, notice that the widths of each are the same width. So it's important to do that. So this width is the same width as that width, which is the same width as that width. Also notice that normally when we see something like this, we think of this as a number line, right? Where this is 0, 1, 2, 3, 4, 5. And that's no longer the case here because in this case, these are categories, right? These are just colors. So, it doesn't belong on a number. Good. So it's just a horizontal line. And then in the vertical direction, we have frequency, how often we saw it. So remember that there were 12. We observed the color the color brown 12 times. So that's why its height goes up to 12. And then the color yellow, we observed it 10 times. And then the color red, we observed it 9 times, I think. And then the color orange is 6 times. Okay, so we can get a visual sense of the table. Good. Good. We can also do the same thing with the relative frequency values, right? The proportions. Again, in order to construct a bar graph, we again put down the colors in the horizontal
we again note that the widths of each rectangle are the same for all of them, and then their heights then go up to a value that represents the proportions. So for browns, right, see, we lose precision because it's not exactly clear how high it is. It looks like it could be 0.27, right, or maybe 0.265, right? I'm not sure. So that's what I was saying, that when we do visual representations of our data, we lose precision very often. Someone that looks at this is not going to be able to get an exact answer, but we do gain is a general perspective of where the data is going, and a general pattern that might emerge from our data. We can easily see that brown and yellow is a lot more popular than blue or green, for instance, right? And as the information gets more and more complicated, it becomes more and more valuable to get rid of some of that precision in exchange for things that identify our patterns, right? As we saw in that little video clip, if you were just presented with all the raw data that showed all the information that was presented, it would have been really difficult, right? Keeping track of incomes and life expectancies and population sizes and regions of the world and the different years. It just would have been a mountain of data and lots of numbers everywhere, and it would have been hard to really see any patterns at all. But by sacrificing all that exact precision in the final version, the final presentation, as I pointed out, we didn't really get any real numbers, or very few real numbers. We got a sense of the data and what was happening, and a pattern of what was going on in the world during the past couple hundred years. Okay, so same thing happens here. This height is supposed to be 0.2667, almost 0.27, but it's kind of hard to know exactly from there, right? So the point is not to be able to look at this bar graph and be able to know the exact height, but we get a good sense, a general sense. Sometimes in order to make it even more precise, you'll see bar graphs that have the actual number up above here, and it might be rounded, so maybe you might see one that has 0.27% like that, so that people can tell, right? So we can always adjust them a little. These graphical representations are a little science, a little art. They take a little bit of finessing, and some people play around with a variety of things to make them more enjoyable and easier to understand. One of the reasons why we insist on all these bars having the same widths is because we are making a connection between area, right? This purple part represents an area, right? It's length times width is the area of this rectangle, and we're letting that area visually represent how many browns were in the bowl, right? So if they all have the same widths, the only thing that changes is their heights, so we can see visually that there were a lot more browns than there were blue. However, if we don't insist on having an equal width, imagine a case where this one is really skinny and the blue is really wide. So even though it doesn't go up very high, it ends up getting a lot of area. So to the eye, it might be a little distracting, and it might not be super clear that there's a lot more brown than there are blues, right? So that's one of the reasons why we insist on the base of each rectangle being the same width. Okay, I think that's pretty self-evident. A Pareto chart is a bar graph where the bars are drawn in decreasing order of frequency or relative frequency. Okay, so there is no particular order to this one, right? It's just colors of in an M&M bag. There's no reason for us to put brown first and then yellow, except maybe that's where the raw data came from in that order. So there might have been a reason for that. Where'd it go? Go back to the raw data. Brown was first and then yellow, so maybe that's why they're written in that order. But instead, if we move around our bars and draw them in a descending fashion with the highest one first, and then the next lowest, and then the next lowest, and the next lowest, so on and so forth, we'll end up with a Pareto chart.
So here's what it would look like if it was a Pareto chart, where we automatically put the biggest one first. So this helps a little bit more with the precision, right? Because like I said, often it's kind of hard to tell visually which one, what the exact numbers are, what the exact values are. But with the Pareto chart, we can at least already see that this one's going to be a little bit bigger than that one, and this one's going to be a little bit bigger than that one, because it's in that order. And again, it just helps to establish the greater pattern this way. Okay, I think that's pretty self-evident as well. Sometimes, we gotta step up our game and increase the complexity of the graphs we create, because the data gets complicated. So one thing that we could do is do a side-by-side bar graph. So suppose that we know that we know whether more people are finishing. Suppose we want to know whether more people are finishing college today than in 1990. We could draw a side-by-side bar graph to compare the data for 2 different years. Data sets should be compared by using relative frequencies, because the different samples and population sizes make comparisons using frequencies difficult or meaningless, right? So as the size of the population increases, we would naturally expect there to be more people to just graduate from high school and graduate from college and everything in between, just because there's more people. But that might not give you a good sense of whether or not more relative people are graduating, right? So proportionally is what we want. What proportion of the population is finishing high school, is going to college, is graduating from college? That's what we're looking at. Okay, so here is a table with the results we want. So, whoa. We're looking at compare different misleading or finishing college. Yeah, college. Comparing 2 data sets. Marital status. What happened to the college? College is over here. Okay, so different example. We'll come back to the college one. The following data represents the marital status in millions of U.S. residents 18 years or older, 1990 to 2006. Draw the side-by-side relative frequency bar graph for each. So in 1990, 40.4 million people categorized themselves as never married, 112.6 million as married, 13.8 million as widowed, and 15.1 million as divorced. Okay, comparing that to 2006, we have these resulting values, right, in millions. So 127.7 million people were married, 13.9 million were widowed, and 22.8 million were divorced. Good. Okay, so we can present that in a nice side-by-side bar graph like this. So we can assign a color scheme to identify the different years. So light blue is 1990, 2006 is the dark blue. So we got to have a little legend on the side so that people that are looking at this for the first time can decipher it. Good. And we can see that never married grew a little. Married decreased a little, and then widowed decreased a little, and divorced increased a little. Notice that this is relative frequency. If we go back and look at our table for frequency values, there were more people married, like the number of actual people married increased from 112.6 million to 127.7 million, so it went up by a little. But if we look at a relative frequency, it actually went down, right? So as a proportion of all the people in 2006, it was a smaller proportion of people that were married, right? So it's important to distinguish the two. Of course, the number of people married went up simply because there's more people in the country. But that doesn't mean that it's growing in popularity. As we could see, it looks like it's decreasing in popularity. slightly less, smaller proportion of the population in 2006 was married as compared to the population in 1990. A slightly smaller proportion is also widowed, so maybe life expectancies are increasing, maybe deaths are decreasing, right? Widowed, somebody died. Divorce rates are much higher, right? So as a proportion of the population, a much higher proportion of the population has categorized themselves as divorced. And also the proportion of the population that has never married is also higher. So it's easier to see a trend of what's happening here. It looks like it's bad news for marriage from lots of different angles. Good. Well, I guess the only one where it's not is widowed, since more people, less people are widowed. Good. So the institution of marriage is not doing well. So it's a nice bar graph though, right? We can digest the information without having to go to specific numbers. Doesn't really matter exactly how tall this light blue one is and exactly how tall this dark blue one is. We can easily observe that it has decreased by a little. And sometimes that's all that matters. Okay, bar graphs may also be drawn with horizontal bars. Horizontal bars are preferable when categorical names are lengthy. Right, so again, it's just a style thing. Okay, so now we can go back to our example with the population with education. So we have data from 1990, data from 2013. We have relative frequency in the horizontal, and then we have the different categories in the vertical. So remember, this is relative frequency. So as a proportion of the population in 1990, that's this dark blue one, how many people identified themselves as not a high school graduate? Okay, so we could see that that's a little less than 25%, or in that ballpark. That was in 1990. And then way below that is the results for 2013. So a lot more people can be identified as having a high school degree, graduated high school, right? Because a lot less people identify themselves as not graduating. Therefore, a lot more people identify themselves as having graduated. Good. Okay, have at least a high school diploma. Okay, at least a high school diploma. That hasn't changed much. Good. And then some college. Okay, a little bit more on a little bit more people in 1990 identified themselves as some college with no degree. And then at least an associate's degree. Okay, that's where we start to win out in 2013. A lot more people identify themselves as having at least an associate's degree. Or also a bachelor's degree, big difference there, and also a graduate degree. So here is where a lot of the advancements have taken place. So people have been, if we took a snapshot of 1990, there's a lot of people that categorize themselves as not a high school graduate, right? By 2013, there's a lot less people that categorize themselves as not a high school graduate. And so, that proportion of people, that population, we can see has been pushed through the educational system. And a lot of them have been pushed into this, right? A lot of that, the percentage, a lot of that percentage has been pushed up to the associate's, bachelor's, or graduate degree. Remember that because these are relative frequencies, then the area of the dark blues, all these areas must add up to 100%, right? It must add up to 1. The areas of all the green ones must also add up to 100. So if you reduce 1, if you push this back, say from here, it's got to appear somewhere else. Maybe it adds up to here or there, or a combination of all of them. So when we beat back this dark blue one, then more dark blue needed to appear someplace else. Right, if we were to do that. Good. Okay, so I think that's pretty self-evident as well. Okay, a pie chart is a circle divided into sectors. Each sector represents a category of data. The area of each sector is proportional to the frequency of the category. So again, we're making a connection between area and the proportion or the ratio of a particular category within a sample or a population. Okay, so for example, the following data represents the marital status of U.S. residents 18 years or older in 2006. Okay, marital status in millions. So 55.3 million said never married, 127.7 million said married, 13.9 million people said divorced, and 22.8 million people identified themselves. 13.9 said widowed, and 22.8 million identified themselves as divorced. Okay, so here is a pie chart. Right, a pie chart is going to go toward relative frequencies, right? So we got to figure out the percentages of each of these. To do that, we got to add all of these up. That'll give us the total number in millions of people that were counted as part of this data set. So if we add them all up and then we divide each one of these by the total, we'll get the percentage or the ratio of each category. So never married is approximately 1/4 the total, 25%. So it ends up being about 1/4 of the pie. Good. Married is the largest one, 127.7, divided by the total of all of these, and that'll give us the 58%, which is the largest one, right? A little bit more than half. So we're making a connection between the area of our slices here and the proportion of each category. Good. Okay, pie charts I think are pretty easy. Let's move on. Organizing qualitative data. Okay, so we're going to organize discrete data into tables. We're going to construct histograms of discrete data, and we're going to organize continuous data in tables, construct histograms of continuous data. We're going to draw stem and leaf plots, and then draw dot plots, identify the shape and distribution. Okay, the first step in summarizing quantitative data is to determine whether the data is discrete or continuous. If the data is discrete and there are relative few different values in the variables, the categories of the data or the classes will be the observations as qualitative data. So what that means is that if we are collecting data and it's numerical in nature and the numbers don't vary too much, like say for example I stop people on the streets and I ask them, how many kids do you have? I think a very popular choice will be either 0 or 1 or 0 or 0 or 1 or 2 or 1 or 3 or 0. Right? These are the types of answers I'm guessing I will receive if I just randomly stop people and ask them. Every once in a while there might be someone that says I have 8 kids, but those are rare. Rare enough to give them TV shows nowadays. But I think most people, personally, I don't really know anybody with a child. Well, that's not true. I do know a couple of people. They're just not very, I don't really spend that much time with them. So in my everyday life, there really isn't any children. I know, I'm lucky that way. So I might see, my guess is that I would see a lot of zeros. Okay, so they're categorical. They're discrete, right? So nice whole numbers. And so if I wanted to come up with a way of describing all this data, then I could just use the actual numbers themselves as the classes. There's not that many of them. Right? So I can do like a tally where I do 0, 1, 2, 3, maybe up to 8. 4, 5, 6, 7, 8. Right? Based on my sample, maybe 8 was just the largest one I ever observed. Doesn't mean that it can't be higher than that. It's just that my data set, I didn't see anything higher than an 8. And I didn't see a 4, a 5, a 6, or a 7 either. But I might want to put them there just to make sure that people see that there was none of those, that it wasn't a mistake or something, right? Because if I just delete them and go 0, 1, 2, 3, 8, then people might wonder what happened there. But again, that's more of an artistic choice. Some people might choose to do that. You just have to pay attention to your table. Okay, and then I can do a tally and see, okay, how many times did I see a 0?
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 times. Right? Of course, that's the frequency. Good. And these are called classes. Okay, now on the other hand, if I stop people on the streets and I ask them something that might, like the numbers might vary a lot. Like I might ask them, on your tax return from last year, how much money did you make? Right? How much did you record? Right? And now the answers might be really different. Somebody might say $37,138.43. Maybe that's one result. That's one. Maybe somebody else says, well, no, I reported $58,193.12. Right? And so on and so forth. And so if I have a big table, I asked 50 people surveyed, I'm going to have 50 numbers, and it's probably true that all 50 people give me 50 different numbers, right? So if I was going to do a table like this, it wouldn't make sense for me to write down each one of them this way. $37,138.43, one person said that. And $58,193.12, one person said that. Like, it's likely I'm going to have 50 different numbers here, and they're all going to say 1 over here, and that's not really going to be very useful, right? So that's when we start to come up with little classes. Instead of saying 37,000, what if instead we just put a little class here that says from 30,000 to 40,000. From 30 to 40,000. Okay, so now as I go through my list, there might be lots of people that were in that group. Maybe I can end up with 10. So in the 50 people, 10 different people said that they reported a number somewhere between 10,000 and 40,000. Now we have to be careful about the next number though, because if I put this one as 40,000 to 50,000, well, now we have a problem with this exact person here. If someone actually reported exactly $40,000, where do we put them? Are they part of this class or are they part of this class? So we have to be extra careful about how we define our classes. We have to define them in a way such that any number that in here can land in exactly one of these and not two of these. So I can't do that. So what I could do is maybe define this thing by a little bit more precision. So to 40,000, and from 40,000 and 1 penny. Right, so right at 40,000, you go in this class. If you get 40,000 and 1 penny, you go in this class. Right? So we're being a little bit more precise with our table. So that's a little bit more useful. Another thing we could do is just round to the nearest whole dollar. Right? And if we round to the nearest whole dollar, so like let's say that this one is just rounded off to 37,138, and this one's rounded off to 58,193. So if we just round to the nearest whole dollar, there's no pennies, then we don't have to worry about this. The other thing we could do then is just cap this off and say that we could say that this is make this 39,999. Right, remember there's no pennies if we just round off everything to the nearest whole dollar, and then this one can go up to from 40,000 moving on. Okay, so we have to be careful about how we create these classes, and we're going to come back to that in a little bit, but just giving you a sense of what we're doing. So we're going to start off with cases where we have a small number of differences in the discrete values, so we can just use those values as our classes. On the other hand, if there's a lot of them, then we want to start grouping them up into classes that are kind of like a range of values. So here's an example. The following data represents the number of available cars in the household based on a random sample of 50 households. So 50 people were randomly asked, how many cars are in your house, right? You know, how many cars are available in the driveway or available to people that live in the house. So somebody said we have 3 cars in the house, 0 cars, 1 car, 2 cars, 1 car, 1 car, 1 car, 2 cars, 0 cars, 2 cars. Okay, so you can see that there's not a lot of variation here. So we can use the actual values as their classes. 0, 1, 2, 3, 4, and 5 are the only numbers we observed. We do a running tally, and we can see that of the 50 people, 4 said 0 cars. Of the 50 people, 13 said 1 car. Of the 50 people, 22 said 2 cars. So it looks like by far the most popular option is 2 cars. And then, because there were 50 total, we divide each one of these numbers by 50, and we get the relative frequency, which is the percentage of our sample. So 8% of our responses said 0 cars. 26% of our responses said 1 car. 44%, a little less than half, said 2 cars, and so on and so forth. Okay, so we know that we can do a variety of things with this information. We can create a pie chart, we know that now, or we can create this histogram. So a histogram is constructed by drawing rectangles for each class of data. The heights of each rectangle is the frequency or the relative frequency of the class, and the width of each rectangle is the same as and the rectangles touch each other, right? So that's the only real difference between this and a bar graph. Very, very similar to a bar graph, except we've decided that we want a histogram. We want the rectangles to touch each other. But it's the same idea that we're going to make a connection between the area of the rectangle and the relative frequency of that category or that class in this case. Good. Okay. So this is what it would look like. So here's a histogram. The histogram looks like this. These are the classes, and because these are discrete values, whole numbers, and there's very few of them, we could just actually use the actual values. We'll see in a second what happens when we can't do that. Okay, and then we can create a table, just like a tally like before, and a relative frequency. And then we create a histogram like this. So it looks a lot like a bar graph, except they're touching each other, right? That's how you know they're touching each other. And this time we don't have we actually do have numbers. But notice that the sort of like the center of this box is the 0, not that one over there. And the center of this rectangle is a 1, and this one's a 2, and a 3, and a 4, and a 5. So it's a little like the classes when we saw brown, yellow, orange, like that, except in this case we actually do have numbers. The heights in this case represent frequency, so I can see that it was about 4 zeros, and can't tell, it looks like maybe like a 13 or 14 ones. Good. And then we can also do the same thing with relative frequency. Relative frequency. And the height represents the ratio, the proportion that we saw. Right? That number was observed approximately this percentage of the time. Right? And again, we're exchanging precision in exchange for a pattern, so I can easily see what the pattern was, rather than the actual values themselves. Good. Okay. Classes are categories into which data are grouped. When a data set consists of a large number of different discrete data values, or when a data set consists of continuous data, we must create classes by using intervals of numbers. So this is what they would look like. For example, ages. The following data represents the number of persons 25 to 36 who are currently working disabled. So if I went out and surveyed the working disabled in the country and I asked them to give me their ages,
the results would be, the data table would be pretty large, right? So the raw data would look a little like this. I go and I found a discrete, a disabled person that works, currently working disabled person, and I asked them their age. They might say I'm 27, and then I found another one and I asked them, what's your age? Okay, I'm 63. What's your age? I'm 32. I'm also 32. I'm 28. Right? So this is what the results would look like. And as you can see that there are thousands of them, a raw table like this with thousands of numbers that kind of danced around between 25 to 64 is what we're looking at. So it would be really difficult to have a table representing the values where each of the numbers is its own class. We'd have 25, 26, 27, 28, 29, 30, 31, right? So that we'd have each one of these going all the way down to 64. So already it would be difficult to kind of digest that data. So rather than writing down one whole class for each of the numbers that are possible, we group them up. And so here's an example. They've been grouped up this way. 25 to 34 is one class. 35 to 44 is another class. 45 to 54 is another class. And 55 to 64 is another class. See, so we've grouped up some of these values. This means that there were 2,132 people that identified themselves as being between 25 to 34 years of age, right? So you could either ask people to sort of check a box, check which one of these boxes applies to you the most, applies to you. Either you're 25 to 34, 35 to 44, 45 to 54, 55 to 64, or you can just plainly ask them, what is your age? And then later, you take all that raw data and you group it up yourself, right? Regardless of how the data was originally gathered, the end result is the same, where we have these classes and we can see the frequency of people within each class. Good. A few definitions. Lower class limits. So within each class, right? Each one of these is a class. Class number 1 is that one. Class number 2 is that one, right? So that thing is the class. Class, class, class. In this example, there's 1, 2, 3, 4 different classes. Good. Okay. Now, all of these lower values are the lower class limits. The 25 is the lower class limit of the first class. 35 is the lower class limit of the second class, and so on and so forth. Collectively, the 25, the 35, the 45, and the 55 are the lower class limits. The upper class limits are exactly what we would expect, the 34, the 44, the 54, and the 64. These collectively represent the upper class limits. Within a specific class, you could say, looking at the class between 45 to 54, you could say the 45 is the lower class limit and 55 is the upper class limit. Okay. Class width. So there's a couple of ways to define this. The class width is the difference between consecutive lower class limits. The class width of the data given above is 35 minus 24 is equal to 10. So we take two consecutive lower class limits, so 25 and 35, and that's how we get the 10. Gives me 10. Nothing special about these two. It could be any one of them. So 55 and 44, 55 minus 45 also gives you 10. Right? So we get the same value, in this instance, a 10 for each one of these. When we are presented with when we're presented with a table already, then we should know that the class widths are going to be the same. Or when we create one ourselves, when we create our own histogram, we have to know that we want the class width to be the same. Okay, let's keep going.
So here's an example of raw data. The following data represents the time between eruptions in seconds for a random sample of 45 eruptions at Old Faithful geyser in Wyoming. So let's see what that is. Some of you might not know. Okay, it's nice and quiet. Okay, so now that we know what we're talking about. Here is data representing the time between eruptions in seconds for a random of 45 eruptions. So in the first case, this means that 728 seconds occurred before the next eruption, and then 678 seconds before the next eruption, and then 728 seconds, and so on and so forth. So it looks fairly consistent, but it's not an exact number, and so they do vary a little bit. So again, one thing we could do is assign a class to each one of these numbers. So when we're creating our table, we can create a table and we can assign a class to each one of these numbers that we see. So like 678 is its own class, and then I don't see any 679, so that there's one question. Should we put down 679 and 680 and 681 and 682? Should we put down each one of these? A lot of these are going to have either just 1 or zeros, so it's not going to be a very pretty table, right? And then also it's going to be pretty long going down here, right? I see, what's the largest number I see? I see a 728, 730, 738, right? So it's going to go all the way to 738 as the largest one I see, I think. And, you know, who knows? There might be one random one that's bigger than that. So it's not going to look very pretty this way, right? So instead what we want to do is put up little groups, little classes, little intervals that capture some of this data. And that, you know, can vary a little bit depending on how you do it. So here's one way to do it. The smallest value of the data is a 672, and the largest value is 738. So we will create the classes so that the lower class limit of the first class is 670. How did we choose 670? Well, it's just a nice whole number, convenient number that's a little bit below our smallest value, right? Creating these things is a little science, a little art. we want to make them pretty. So we want to be able to either use the smallest number or something a little bit lower than that makes sense. Good. Now we got to get the right class width. The class width we can get by taking the range, which is going to be the difference between the smallest and the largest one, and then dividing it by the number of classes that we want to see so we can see the class width. Good. So just to begin with now, we can just kind of arbitrarily start with 10. Doesn't have to be that, but could be a good choice. So if we want the class width to be 10, remember that the class width is the width or the difference between two consecutive lower class limits. So if I add 10 to this, because that's what I want my class width to be, that's how I get to 680. And I want them all to be the same, so that's how I can create all of these guys. Right? So start with either the lowest number or a convenient value a little bit below that. And then we want to figure out what's the class width we want. We'll get back to this in a little bit, but for now let's just say it's 10. Okay, so we add 10 each time. And then once we've constructed all the lower class bounds for the categories we want, for the classes we want, now we got to come back and we got to find all the upper class limits. Remember not to make the mistake of saying 680, because if you say 680, then if we specifically see the value of 680 in our group data, in our raw data, we won't know which class it belongs to. So we got to go a little bit below that. We could choose 679, or we could be even more precise if we want to and say it's 679.9, for example. But if we look at our raw data, it was only whole numbers, so we don't have to go that much more precise, right? There's nothing wrong with using 179.9. It's just unnecessarily precise. We don't need to go to that level of precision. Since our raw data was only whole numbers, we should only go up to that level of precision, up to a whole number, and leave it at 179. If all of these numbers did have a decimal, like let's say for a second that all of these had a decimal behind it, 0.3, 0.7, 0.2, 0.9, 0.8. So if they have one decimal level of precision, then we should come back here and make sure that this has one decimal of precision as well. Good. So this one, this would do it for us. Okay. So once we do that, it's easy to finish up our classes, and then it's time to make sure that it all worked out, because we have to confirm that that the classes fit our data. We want to make sure that the largest number really does fall in the last class. Sometimes, based on the data, we might end up with something weird, where maybe the largest value doesn't quite fit into one of these. Also, just double check that every value in our raw data set fits into exactly one of these classes. Sometimes we refer to them as bins, so that we can do a proper tally for these. Okay. So once we have our different classes, we can go back through our data and create a little tally. So this, for example, the very first value in our table was 728. 728 is going to land right in here. So that's where this one little dash would come from, 728. Okay, one value there. And then we go back to our table and find another one, right? So every one of those values in our raw data should fall in exactly one of these classes. So we can create our tally, and then we can find our frequency, and then we can find our relative frequency, right? All those things will help us create our histogram. Okay. The choice of the lower class limit is the first class, in the first class, and the class width are rather arbitrary. Sorry. The choices of the lower class limits of the first class and the class width were rather arbitrary. So like I said, it's a little bit of art, a little bit of science. There's not an exact perfect way of doing it. You just got to fudge around with it and change it around a little bit until you see something that's useful.
There is not one correct frequency distribution for the particular data set. However, some frequency distributions can better illustrate patterns within the data than others. So constructing a frequency distribution is somewhat of an art form. Okay, so here's another example where instead of using a class width of 10, we can use a class width of 5. Right? We went from 670 to 675, 680, 685, so on and so forth. And now we go back and we group up our values. So remember, the first one was 728. That means that 728 lands right here, and that's how that little dash happens right there for 728. Good. So we do all the other numbers on here, all 45 of them, and we come up with our distribution, frequency distribution table, right? Our frequencies and our relative frequencies. But you know, notice that by doing it, by having a class width of 5, this is where we have a class width equals to 5, we end up getting a couple of ones here, several zeros over here, and when we had it with class width of 10, we only had one class that was a 0, and then these two were kind of grouped up into one single class, and this is where we had a class width of 10. Good. Okay, which one's better? I don't know. It's kind of up to you to decide. It's a little bit of art, a little bit of science. So you got to present it in a way that you think does the best job of presenting the data. Good. So you can manipulate that a little bit. As far as our homework goes, they usually tell you what to do. And so the class width is often connected with how many classes we want. Right here we ended up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 different classes. Right? Whereas over here we ended up with 1, 2, 3, 4, 5, 6, 7 classes. Right? So do we want 7 classes? Does that do a good job of representing our data? Or do we want to go with more classes? Generally, the bigger the raw data set is, the more classes you're going to want. And the smaller it is, the less classes you want. But usually we want something in between 4 to 20 classes or so. Okay, choosing the lower class limit of the first class, choose the smallest observation in the data, or a value that's conveniently slightly lower. Good. The class width, we want to take the largest class value minus the smallest class value and divide by the number of classes that we're going to want. And we usually want somewhere between 5 to 20. That we've found that's generally a good number of classes for the data would fall somewhere there. The larger the data set is, the original raw data set, the more classes we want. So if we had a file that had 100,000 results, 20 classes seems pretty good. 5 classes would be too little. Okay. On the other hand, if we only have a data set of 30 things, we don't want 20 classes to describe a data set of 20 items. Right? If I asked everyone in class to tell me their age, what kind of results would I get? Ages for students in class. Okay, so somebody says I'm 21, I'm 18, I'm 19, I'm 18, I'm 23, I'm 45, I'm whatever. So these are the results I would get. If I had 30 students and I wanted to do a histogram with all these, it wouldn't make sense for me to have 20 different classes for 30 students, right? On the other hand, if I did this for the entire college would have, approximately 20,000 students. So 5 classes would really not do a very good job of representing the data, 20,000 data points. Good. Okay, so somewhere in between 5 to 20, you can play around with it until you get a good result. As far as our homework goes, though, they usually tell you what to do. So follow the instructions for the homework. Guidelines for determining the lower class limit. So round this value up to a convenient number. determining the lower class limit of the first class in the class width. Round this value up to a convenient number. Oh, the class width. Oh, sorry. This thing is weird. The class width, a general guideline for creating the class width is this, and then they want you to round this class width number up to a nice convenient number. So our table from above, our histogram, looks like this with a class width of 10. And then if we have a class width of 5, it looks like this. So you can see, one is, they're a little bit different. They both do a pretty good job. Wait, no, these are both, this is class width of 10, and this is a frequency. And then over here we have a relative frequency. They both give you the same interpretation of the data, I think. And now if we had a class with a 5, we see we end up with more classes, bins. And so the data looks a little bit different than over here. Right? Here it looked more like a consistent sort of wall of bars. Whereas now if we break them up, we see that they're not quite so consistent. These things are really high, and then there's like a big drop off right there. And then, it builds up differently. So we can see a little bit more variation. So someone might favor this a little bit more than this one, depending on what it is they want to showcase. Right? So that's where the art form comes in. As far as your homework, just follow the instructions. Let's see, there's another app for this that I wanted to point out. So let's get rid of that. So here is another example. We have a bunch of scores here. Right, this is just random sample of 34 scores, and just this app automatically creates a histogram for us. So histogram, and this is with 23 bins. So if we come back over here and say let's do 5 bins, 5 classes. Then we can see that this data set here creates this. So when we look at the raw data like this, all these random numbers, it might be kind of hard to spot what the patterns are. But when we do this histogram, we can see that a lot of those decimals seem to dance around here. Right? That's the general pattern. So they're kind of consistently building up to that. Good. And that's with 5 bins. If we increase it a little bit more, let's jump over to 10. This is what that same data would look like if we break it up into 10 different classes. And then that same data would look like this if we broke it up into 20 different classes. Come on. Come on. 20 different classes. Good. And then if we went all the way out to 34, whoops. Went all the way out to 34, 34 classes, it would look like this. Good, 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 good. All right, so as we increase the number of bins, you can see that we start to get strange data. Actually, I'm not really sure why it's doing that. Let's put in our own data. What's this? So 798, 730, 726, 698, 721, 722, 700, 720, 729, 678, 722, 760.
718, 702, 703, 718, 703, 718, 703, 699. Okay, so I uploaded all our data for the time lapse between eruptions at Old Faithful, so we can use this data, and the system automatically creates our histograms. So if we just had just one bin, then all our values would land between, I think the smallest one was what, 672 was the smallest value, and 738. So all values land there, just one giant rectangle that contains all the data. That's incredibly useless, right? There's nothing you can really draw from, very little you can draw from there, except we can see that all of them land somewhere between these two values. Okay, so then as we increase the number of bins, okay, so we start to get a little bit more information from our data. But 2 bins is not enough, so we say the minimum should be about 5. So here with 5 bins, we can see what's happening, the pattern. Looks like around 680, the lower values are pretty rare. It looks like right around 700 to 720, those seem to be pretty popular results. And then as we go higher and higher and higher with the number of bins, we start to really lose quality of data until it just gets kind of silly. Right? There's little we can tell from that. We were able to tell a lot more when we had just a few bins, maybe around 5 or 6. Right? So which one of these is the best one is a little bit up to you, depending on sort of your own ideas of what pattern you think, which graph do you think does a good job of describing the patterns. But as far as the homework goes, just follow the instructions, and it should give you that information. Good. Okay, so we have the data from our thing. What is this random sample? Oh, okay, never mind. I know what that is. All right, back to this guy. Okay, stem and leaf displays. Okay, an individual is considered to be unemployed if they do not have a job but are actively seeking employment. The following data represents the unemployment rate of each of the 50 states plus the District of Columbia. So we're going to have 51 values, right? So 50 states plus the District of Columbia is going to mean that we have 51 results. And here they are. Here's the 51 results. So in Alabama, 4.7%. In Alaska, 6.8%. Arizona, 4.8%. California, 6.9%. Okay, so here are all our results. One way of presenting all of this is with a stem and leaf display. And so here's what a stem and leaf display is. We let the stem represent the integer portion of the number, so the first number of our value, and the leaf will be that decimal portion, right? So for example, 4.7, we have the 4 is going to be the stem, and the 7 is going to be the leaf, right? Okay, and so this is what it looks like. The 4.7 is these two, the 4.7. Good. So that means that there's a 4.8 and a 4.2 and a 4. Right? So when we see a 0, that means that's 4.0. Good. Okay, so these numbers over here are the ones we call the stems. Stem is these numbers, the 2, the 3, the 4, the 5. And the leaves are these values over here, the decimal last points. Leaves are these guys. And again, it makes it easier to digest the data and see patterns, right? So I can see that looks like 5 point something is the most popular one. And then 4 point something and 6 point something are also pretty popular. 7 point something and 8 point something are pretty unpopular, and 2.8 is also very unpopular. Good, so we can see that there's a nice little shape here, little mountain on the side here, little vertical mountain here. Good. Okay, I think that's pretty straightforward. Stem and leaf display. So to construct one, the stem of the data will consist of the digits to the left of the rightmost digit, right? So stem and leaf display, we're gonna separate the very last digit from the rest of the number. The rest of the number is gonna be the stem, and just that last digit is the leaf. So if the data consisted of, say, GPAs, I asked people, hey, what's your GPA? 3.39, 4.00. Maybe somebody says 3.87. So, right? So in this case, we have 2 decimal points. So when we create our stem is going to be this part here. The last digit is going to be the leaf. Good. So when we create our display, we might have 4.0, 4.1, oops, not 4.1. Wish you had a 4.1. 3.9, 3.8, 3.7, 3.6, 3.5, 3.4, 3.3, right? And then like this. And then if we have like a 1 here, that means that I guess with this one you'd have only the 0, huh? Okay, so if we had a 7 here, that means somebody got a 3.97. We had a 2, so that means somebody got a 3.92. So this 3.39, that would be 3.39, and 3.87, 3.87 would go there. Good. Okay, so this decimal is a little awkward, so maybe people might just ignore it and just write the 4, 0, 39, 38, 38, 37, and just kind of expect you to understand what that means. Or there might be a little explanation on the side to let you know that 3.97 is 3.97. So there might be a little thing about divide the number by something, or an explanation of what that means. But I think the most popular thing would be just to leave the decimal in place. Right? It's just a matter of which one makes the most amount of sense. Good. Okay. So write each leaf corresponding to the stem on the right. Within each stem, rearrange the leaves in ascending order. Title the plot. Okay, so once we've already put them all, identified them all, then they might be in a random order here. So it'd be nice if we organize them from the smallest to the largest, or the other way around. So that's what this is here, for example. Here's a stem and leaf display where these things are kind of in sort of a chaotic mess. That means that there was 147, 148, another 42. But now if we organize these from smallest to largest, we see that there were 1, 2, 3, 4 different times we saw a 40, and 1, 2, 3 different times we saw a 32. So it's easier to see the pattern of the overall data, but then also maybe spot which numbers appeared most often. We can see 40 was very popular. We can see that 53 was very popular. And also it makes it easier now to write these in order, from the smallest to the largest. So if I was going to write these from the smallest to the largest, now I can see that they would translate into a 28, then a 32, and then another 32, and then another 32. 1, 2, 3 different times. 1, 2, 3. And then a 33, and then a 38, and then another 38, and then another 38. 1, 2, 3 different 38s. Then 2 different 39s. A 39 followed by another 39. And then a couple of 40s. 1, 2, 3, 4 40s. So 40, 40, 40, and 40. Okay, so I can keep going that way. So this helps me see pretty easily a pattern of all the numbers, sort of where the bulk of the values are, which one's the most popular numbers, which one specifically, which number appeared the most, or kind of spot the ones that were most popular. And also lets me write them down from the smallest to the largest in a very easy way. Good. So those are stem and leaf plots, stem and leaf displays. When data appeared rather bunched, we can use split stem. So stem and leaf display shown on the next slide reveals the distribution of the data better. As with the determination of class intervals and the creation of frequency histograms, judgment plays a major role. So there's no such thing as a correct one. All right, so here is a split one. So instead of just having the 20s, the 30s, the 40s, what we could do is separate them so that maybe we go from 0 through 4 on one of them, and then 5 through 9 on the other one, so we can separate them a little bit more. Good. So that's going back to this thing. See how there's a lot of values in the 30s, a lot of values in the 40s? So all they've done here is kept this 2, and then this, the 32, the 32, the 32, the 33, the 38, they're separated into 2 different ones, where all the ones that land between 0, 1, 2, 3, and 4 go on the first one, and then 5, 6, 7, 8, or 9 go on the second one. So we're going to end up with 1, 2, 3, and a 3, and then 1, 2, 3, 9, 9 in the next one. Good. And then 4 and 4, and same thing. We want to keep all the ones that go from 0, 1, 2, 3, or 4 on the first one, and then the other ones on the second one. So this would be 1, 2, 3, 4 zeros, a 1, a 2, a 3, and a 4. And then there's a 6, 7, 7, 8. Good. That's what the split one was. Good. Okay.
Advantage of the stem and leaf display of the histogram. Once a frequency distribution or histogram of continuous data is created, the raw data is lost unless reported with a frequency distribution. However, the raw data can be retrieved from a stem and leaf display, right? So once we create our histogram, let's go back to one of these things. Here's a histogram. I display it. I present it to someone. The original data is we're unable to retrieve it from here. I can see that there was one value in this class, but it's hard to know exactly what that number was, right? I can see that there was about 7 values that were in this class, but again, it's hard to see exactly what the original data is. Okay. All right. So, but with a stem and leaf display, we can always come back and get the original data. Once the final presentation is created, the original data is not lost. So that's one advantage to a stem and leaf display. Similar to these is a dot plot. A dot plot is drawn by placing each observation horizontally in increasing order and placing a dot above the observation each time it is observed. Right? It's the easiest of them all. So here we have a data set. This was available cars in households of 50 households. So somebody had 3 available cars, 0 available cars, 1 available car, 2 available cars, 1 available car, so on and so forth. 50 households. And so now to create a dot plot, you just have to go the results in the horizontal line. Somebody said 0, 1, 2, 3, 4, 5. Nobody said higher than that. So that's why we include only 0, 1, 2, 3, 4, and 5. And then as you're going through your data set, all you have to do is put a little dot above each value when you see it. So because somebody said, 5, then that's where this little dot comes in, one little dot there. And then somebody said 3, so we put one little dot right there at 3. Somebody said 1, so we put a little dot there at 1, and so on and so forth. So you can see that when the number is repeated, they stack. So we can start to see that the tallest stack is the one that appeared most often. And then this also preserves the original data, right? If this was given to me, I can reconstruct it, I can deconstruct it, and go back to the original raw data file, right? So that's another nice thing about dot plots. Although if there's a lot of them, it might be really difficult to go back, but it's not impossible. Good. The shapes of the data. So often we're just getting a general sense of the data, the shape of it, a pattern that might emerge. So there's a couple of general patterns of graphs that we pay special attention to. One of them is called a uniform distribution. Right? This is the frequency of each value of the variable is evenly spread out across the variables, right? Uniform. Everyone is the same. So across the different classes, they're all about the same. Bell shape is the most famous, right? It looks like a little mountain. Starts off small, builds up to some highest value toward the middle, and then comes back down and tails off like a little mountain, right? And this would be where it's kind of equally distributed. And then we have something that's a little like a mountain, except it's skewed right. The tail right of the peak is longer than the tail of the right of the peak is longer than the tail on the left peak. So just as a general shape of these graphs, so let's say I have a graph that's here. So a uniform graph would look like this, approximately, right? All the different classes are here. Here's one class, here's another class, here's another class, and they're all about the same. I mean, it might be exactly the same or something close. Maybe the next class is like right there, so it's almost the same, right? So it doesn't have to be exactly the same, but, pretty close to the same. So either uniform or approximately uniform. But they all have approximately the same values across each of the classes. Good. On the other hand, if we were looking at a bell-shaped distribution, this would be something where they kind of build up. The classes kind of build up. So it could be something that kind of goes like this. Or approximately that much. So we could do it with categories like this. And there might be, let's say, another one over here, and then another one over there, and then another one. something like this, where it's approximately a bell shape, builds up to the highest value somewhere near the middle and comes back down. Right? And then we call these tails. So this is the left tail and the right tail. So in a right skewed graph, it means that the tail on the right seems to be longer than the one on the left. So if the graph looked more like this, where it kind of builds, but not so much, right? So there seems to be a much longer tail in that direction than in this direction. It just kind of went like that. So this is a right tail screw. And then a left tail is the opposite. The tail to the left of the peak is longer than the one to the right. So maybe there's more of a build-up over here. Oops. Okay, maybe there's a build-up. Whoa. And then not so much on the right. So there's a little build up to a maximum, and then it just kind of dropped off more quickly. Good. So left tail, right tail. Good, 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 good. If we did this with so many bins, there's so many classes, eventually they just kind of, from far away, they just look like a smooth curvature, right? If there's so many of these tiny little bins, so many of them, it might look like a nice smooth curvature. Or when we get to continuous data, then this would look a little more like this, right? So this is a nice bell-shaped distribution, whereas a right tail one would be one where it kind of goes up quickly and then slowly goes that way. And then finally, a left tail one is the opposite, where it slowly builds up to something and then kind of tapers off. Good. All right, so here's some examples. A uniform distribution, right? Then we have a bell-shaped distribution, or approximately bell-shaped. Let's zoom in. So it kind of builds up to some peak and comes back down. Here we have a distribution that's skewed right. It seems to be a little tail that goes this way. And here's one where it's skewed left. The left tail is slowly building up and then kind of comes down faster. Identifying shapes of distributions. Identify the shape of the following histogram, which represents a time between eruptions of Old Faithful. Okay, so we look at our graph like this. So because it, feel like it's kind of building up this way and then kind of comes off this way, I would say that this is going to be left-tailed. And as we saw when we break it up, there's slightly different ways of looking at it. I think this was the original data as well over here. So here it is with 5 bins, with 6 bins, with 7 bins, 8 bins, right? So depending on the actual number of classes you choose, the data might look a little bit different. This is where you have to be careful, creative, depends, right? So the field of statistics can be manipulated a little bit to kind of describe things in different ways, so you have to be careful about that. Okay, the last section in this chapter is going to be 2.3. And in this section, we're going to look at constructing frequency polygons. So what is a frequency polygon and how to construct one. I want to create cumulative frequency and relative frequency tables, and we're going to construct frequency and relative frequency ogives, and also look at time series graphs. Okay, so this is a pretty easy section. First, we need to define what's a class midpoint. So remember that classes are kind of like those little categories that we group up our data into. So we have lower class points, upper class points. We've already defined those. So class midpoint is the sum of two consecutive lower class limits, and then we divide that by 2. The difference between two consecutive class limits was the class width. So remember that, for example, if we had 680, 690, 700, 710, and then this one went up to 689, and this one went up to 699, and this one went to 709, and this one went to 719. Let's say we had these classes, 1, 2, 3, 4 different classes. Then all of these numbers, the 680, 690, 700, 710, these would be the lower class limits. And then the 789, 799, 709, and the 719 would be the upper class limits. The class width is found by subtracting any two consecutive values. So the class width, would be 710 minus 700, which would give me 10. Or likewise, I could do 700 minus 690, which is also 10. Right, so that's how we find our class width. We subtract two consecutive lower class limits. And now the class midpoint is found by adding two consecutive lower class limits and then dividing by 2. So the midpoint for the first one here is going to be found by adding 680 plus 690 and dividing by 2. So that would get us to 680 plus 690 gets us to 1370. Divide that by 2. Divide that by 2 gets us to 685. So the class midpoint of this first one is going to be 685. Right? Class midpoint between these two. So I grabbed these two, and then that would make it the class midpoint here. So the midpoint is going to be different for each class. I'm going to have to kind of come up with its own like this. And so 685 is the class midpoint for the first category. To find the class midpoint of the next one, I got to do 700 plus 690. 690 plus 700, divide that by 2, right? And that'll be 1390. 700 plus 690 would be 1390. Divide that by 2. Divide that by 2 gets me to the 695, just as expected. That becomes the class midpoint here. And then you start to see a pattern. So this is going to be 605, and this is going to be 705 and 715. Good. So these are the different class midpoints. Okay, so now that we know how to get the class midpoints, then we can use that information along with our frequency and relative frequencies to create frequency polygons. So a frequency polygon is a graph that uses the points connected by line segments to represent the frequencies for the classes. It is constructed by plotting a point above each class midpoint on a horizontal axis at a height equal to the frequency of the class. Next, line segments are drawn to connect the consecutive points, and then 2 additional line segments are drawn to connect each of the end graphs to the horizontal axes. Okay, so here's an example. 70, 80, 90, 700, 710, 720, 730. Okay, so these are all the lower class levels, upper class limits. Good. So in the first class, if we add 670 and 680 together and divide by 2, we'll get to 675, the class limit for the first class. If we add 680 and 690 divided by 2, we'll get 685, and then 695, and then 605, 615, 625, right? So that's how we find all the class midpoints. We have the frequencies and the relative frequencies from before. These are the eruptions for Old Faithful. Good. Okay, so now we're going to create a frequency polygon this way. So the first class midpoint is 675, and that's what this value is right here. 675 is that first class midpoint. 685 was the next class midpoint. 695, 705, 715, 725, and 735. Those are all the class midpoints that we just found from here. 675, 685, 695. Okay, and then above 675, we're going to go up to 2, since the frequency is a 2. Above the 685, we go up to 0. So that's why this goes up to a 2, then a 0. And then the next value is a 7. So 695 goes up to 7. This height's a 7. So that's how we get all these individual dots, right? It's the frequency above this graph, above the class midpoint. And then finally we connect all of those dots with little line segments. And then the final 2 line segments are connected to the x-axis by following the pattern already established with the class midpoints. So looking at the class midpoints, you can easily guess what the next one's going to be. 675, 685, 690, 705, 715. So I can see that the next one's going to be 745. And I can see that the one right before it would have been 685. And so just making a guess based on that pattern, I can see that this guy is going to be right there at 745, and that this guy is 665. Good. So then you make a connection over to 0 for each one of those, from there all the way down to there. Good. So that's a frequency polygon. And then we can also do the same or similar thing with relative frequency polygons. What is going on here? So relative frequency polygon. So again, we use the same midpoints of each class in the horizontal axes. And now the dot that we create above it refers to the relative frequency value associated with that class. So for the first class, go back over here, there were 2 values there. And then when we divided by the total, we got 0.044. So a little bit more than 4% of the time, we got a result that was in this class. Good. And so that means that this height here would go a little bit lower than 4%, a little bit higher than 4%. So it's a little bit below that 5. Again, we're losing precision. That's often what happens with graphs. Good. There was 0 for 685. And then for 695, there were 7. Divided by the total, it's a little bit more than 15%. And that's what belongs right here. A little bit more than 15%. And then about 20%. Good. Okay, so then we connect all those dots. And again, we make that final connection by drawing a line that connects that last dot to the x-axis, approximately where the next value would have gone in the class midpoints. Okay, so those are frequency polygons. A cumulative frequency distribution displays the aggregate frequency of the categories. In other words, for discrete data, it displays the total number of observations less than or equal to that category. It's the running total, the running sum up to that value. For continuous data, it displays the total number of observations less than or equal to the upper class limit of that class. Good. A cumulative relative frequency distribution displays the proportion or percentage of the observations less than or equal to the category for discrete data, and for proportion or percentage of observations less than or equal to the upper class limit of the continuous data. Okay, what does that mean? Okay, so let's go back to the eruption. So here are our classes. Frequency, 2 values landed in that class. At 0 times did we see an observation that landed in this one. But if we look at the cumulative frequency, sort of the running total, in the first class we saw 2 values, and then in the next class we saw 0. That means that there's still 2. 2 is less than 89. Twice we saw values that were less than 89. The next class we saw 7 results that landed in between 690 and 699, but the running total is 9. Good. So for each one of these values here, so we get the 9, we have to add 7 plus 0 plus 2, and that's how we get 9. To get to the next one, it's the running total, so now we see that there were 9 observations that landed in this class. So if we add all of these numbers, we see that there was a total of 18 up to and including 709 and below, right? Good. Okay, so that's how we get the cumulative frequencies. And then if we divide each one of those by the total number, we get the cumulative relative frequency. So we could say that 4.44% of the observations were less than or equal to 689. Good. About 20% of the observations were less than 699. About 60% of the observations were less than 719. Right? So that's what that cumulative relative frequency means. And then, of course, the last number has to be 1 because it's the running total and it runs up to 100%. For the cumulative relative frequency, this has to add up to 1 at the end there. And for the cumulative frequency, that number there has to add up to the total number of observations. So that's the running count. So we can say that there was a total of 45 observations that were equal to or less than 739. And yeah, there were 45 observations in our raw data set. Good. And OHIV is a graph that represents the cumulative frequencies or cumulative relative frequencies for the class. It is constructed by plotting points in the x-axis under the upper class limits and whose y-coordinates are the cumulative frequencies or cumulative relative frequencies of the class. Okay. In addition, the line segments are drawn connecting the first point to the horizontal axis, so very similar to before. Okay, so again, we have the horizontal axes, again, identifying all the class midpoints. And now we have a dot above here. This represents that there were 2 values in this class. And then the running total would mean that we still stay at 2 for this one. That means that there was no increase between 675 and 685. That means there were 0 observations in the class that has a 685 as its midpoint. Good. And then the next value and the next value and the next value all above their class midpoints. Finally, we connect the dots. And we connect this first one back down to the x-axis, but we do not connect the last one down to the x-axis. Good. So this is cumulative frequency, and then we can also have cumulative relative frequency. So now we're looking at proportions or ratios or percentages. So there was a little bit more than 4% above the 675, no increase for the 685, and then an increase for the 695, and so on and so forth, until we get to here, which means 100%, right? 100% of the values are being considered, are under consideration with this graph. Okay. Almost done. So if the value of the variables is measured at different points in time, the data is referred to as a time series data. Very, very popular. Most popular one is probably like looking at graphs of the stock market over time. Right? It could be throughout the day, looking at the values of the stock, or it could be values throughout the year, or years, decades. So it could vary, but it's very common that we see the values of stocks across time. A time series plot is obtained by plotting the time at which the variable is observed on the horizontal axis and the corresponding value of the variable on the vertical axis. So very, very common. So here's an example. The data to the right shows the closing prices of the Dow Jones Industrial Average for the years of 1990 to 2007. So the final closing value, the last day of trade for each of these calendar years. So in 1990, it was at 2,753. In 1991, that was 2,633. So it looks like we're down a little bit. 1992, 3,100, and 3,300, 3,800, right? So it looks like it's steadily climbing. 7,900. And then in 2000, it reached 11,497 with 12 cents. So just in those 10 years, it almost multiplied by 4. Take this number, multiply by 4, and you get to this number, right? And then it declined a little, and it declined a little more, and it went up a little, went up a little more, a little more, and then this is where it was at in 2007, right? And then of course the following year it went down quite a bit. and then it's been climbing up since then. So there's a table. So we can express that by identifying the calendar years in this direction, and then the results above them, little dots indicating the closing values, and again little lines to connect them, so it's a little easier to visualize what's happening with the closing values of the Dow Jones Industrial. And then also, this can get a little messy here, so another alternative that's very popular is to simply count how many years after 1990. So we'd say number of years since 1990, and then so we would put here, instead of putting 1990, we would just put 0 because it's the 1990 value. Instead of 1991, we could just put a 1, and then a 2, then a 3, then a 4, then a 5, then a 6, right? So it makes it a little nicer than the year. Well, I mean, depends on your perspective, right? You might think it looks a little nicer, you might not. So it's a popular thing to look out for, though. It's something that people often do. Okay, so that kind of concludes the various types of graphs that we're going to be working with in homework. So hopefully not too difficult. Follow the instructions. And let's leave off with one more example of what the pros are doing. Right, so this is what we want to graduate to be able to do cool things like this. So here's another clip of someone using graphs and tables to describe complicated things in a way that's easily digestible.
I'm going to show you where extreme poverty has been and how it has decreased. This is the world, and here are the population back in 1800 in each of the regions, in total 1 billion. Here is the yardstick of income. And I'm going to put down these people to show their incomes. First Europe, and they spread out here, and then Americas on top of that, then come Africa, and on top of it the most populous region, Asia, including Australia. And as I showed you before, almost all people there were living in extreme poverty, on all regions in the world. Now, I'm going to show you what has happened. I start the world, and look, with the Industrial Revolution, the population grew here and the incomes expanded here, mainly because of increased income in Europe and America. And then in the 20th century, population continued to grow here and incomes increased even more. And that changed the whole pattern of the world. It became a divided world. The worldview you grew up with the rich West here and with poor Africa and Asia. But in the 1980s, the amazing growth of China and the other tiger economy in Asia and India, they start to get out of poverty. They close this gap, and they are coming over on this side, and the shape of the world changed again. And look now, Africa is following. I call them the lion economies of Africa. And here we are today in a completely new shape of the world. For those of you who still think about the world as the rich and the poor, I'm going to give you a new concept. I'm going to give you a new term, the middle. What we have to do is to look at those who recently came from extreme poverty and into the middle, to learn what does it take to go from here to there.
Okay, so that's a good place to come to an end. There is another section in Chapter 2 that we are not going to do, so don't worry about it. So tackle your homework and let me know if you have any problems with anything. Okay, next we're going to move on to Chapter 3.